Chapter 2, Basic Electronics and Units of Measure. Introduction. This chapter lays the foundation for your understanding of electronics. This unit introduces you to the fundamental concepts, terms, and units of measure common to all electronics technology. The material presented forms the basis for all subsequent studies in electronics. So the information here in Chapter 2 is very foundational to your understanding of electronics. Okay, first of all, we're going to look at atomic structure. All matter is composed of increasingly smaller building blocks. Those building blocks are, and there's mention here of the building blocks of matter. I'm going to let you read through the first few here. If you want to press your pause button and stop and read through those, please go ahead. I'm going to pick up on down here at electrons. Electrons, negatively charged particle orbiting the nucleus of all atoms. That's what an electron is. A proton, positively charged particle in the nucleus of all atoms. And a neutron, atomic particle having no charge located in the nucleus of an atom. Okay, atomic structure. Below is a hydrogen atom. Atoms can be viewed as a miniature planetary system, similar in concept to our solar system. So here we have a single hydrogen atom, and here is a larger, and you get the idea here of the miniature planetary system. Each atom has a dense nucleus which contains the protons and the neutrons. This is this area right here. Electrons orbit the nucleus of an atom. Okay, notice here the electrons orbit the nucleus of an atom, and an electron has a minute mass compared to the nucleus. A given atom has a definite number of orbiting electrons and a definite number of protons and neutrons. The atom has equal amounts of protons and electrons, so the atom has no net charge. Okay, notice it has an equal amount of electrons which are negatively charged and an equal number of protons which are positively charged. Note over here, electrons can only travel in orbits that have certain dimensions. Each orbit level is called a shell. Only a certain number of electrons per shell are allowed, and we'll be looking specifically at copper later in this lesson to see what we're talking about there. The more energy an electron has, the higher its orbit. So here we have it. We only see one orbit here. Oftentimes there are going to be many orbits. To go to a higher orbit, an electron must gain energy. If an outer orbit electron gains sufficient energy, it can break away from its parent atom. Okay, so here we see this electron that's orbiting around this nucleus, and if it gains sufficient energy, notice here, if it was to gain sufficient energy, suddenly it's out here somewhere, and it has become what is referred to as a free electron. And dissociated electrons become free electrons, and free electrons play key roles in electronics. Atomic structure terms. Now, we've mentioned some of these already, but let's just quickly mention them. Electrons, minute mass compared to protons and neutrons. They're very tiny comparatively. Under normal conditions, an atom has equal number of electrons and protons, so there's no net charge. Shell, allowable orbit levels of electrons. There are a fixed number of electrons in any given shell, so oftentimes what you'll see is you'll have a nucleus and then you'll have several shells that contain the electrons, and they're drawn more, they're better drawn than that, but that gives you the idea. Free electrons. an electron with sufficient energy to break away from its parent atom. So this would be an electron out here in the outer valence shell, and it has sufficient energy that it actually breaks away from the parent atom. Valence electron, an electron in the outermost orbit of an atom, and that's what we were talking about, the guy that's going around here in the outermost orbit. Ion, an atom that has lost or gained an electron. So in the case of this, if this atom or this electron gets away from this atom, then this atom becomes what is referred to as a positive ion, because now it has more positive charges than negative. An atom that has lost an electron is a positive ion. An atom that has gained an electron is a negative ion. Okay, classes of materials. Materials can be classified by their ability to pass electrical current. And we have 4 that we want to pay attention to. We're going to look at each of these in a little more detail, but let's introduce them. First of all, insulators. These are materials that have few free electrons and do not conduct electricity well. Conductors. These are materials with loosely bound valence electrons where little energy is required to free them. This is in the case of many metals. Semiconductors. These are materials that are neither good insulators nor good conductors. So these are, the idea of a semiconductor is they kind of conduct because they don't conduct very well. They don't insulate very well. They're in a class we call semiconductors. Semiconductors have 4 valence electrons and are represented by germanium and silicon. Superconductors, these are materials that offer no opposition to current flow, essentially being perfect conductors. The charge of a material is determined by having more or fewer electrons than protons. Materials with an excess of electrons are negatively charged. Materials with a deficiency of electrons are positively charged. Okay, let's talk about insulators. Insulators have 8 electrons in their outer valence shell, and this is the max that you can have in the outer shell, and this is called, actually the term they use to describe this is that it is bound, and this is not a very good picture, but in the outer valence electron it should be perfectly circular. Here you would have 8 electrons, and this is referred to as being bound. It is very stable and does not take part in chemical reactions. And so these electrons, they simply are not going to be able to move. They're freed, they're bound into their particular orbit, and they're not going to go anywhere. Use in electronic circuits to prevent flow of electricity. These are commonly used in, for example, in high power lines. Will connect to their poles through an insulator because they don't want the voltage to, short out to ground, so they connect them to insulators. Insulators are typically mica, glass, plastic, rubber, Teflon, and air. Okay, in contrast to insulators, we have conductors, and materials such as copper, gold, silver, and aluminum. Most metals have loosely bound valence electrons. So in this case, if we were looking at that outer shell, there is only 1 out there, 1 electron in that outer orbit. At room temperature, many of the copper valence electrons are free. So this guy at room temperature, there's enough energy so that it may be moving. And if you had, if you have a whole bunch of copper atoms together and they all have their their little valence electron here within the within copper, you may at room temperature you're going to have the movement of these electrons. They're just going to be moving around. They won't have any particular direction, but they will be moving. When we actually induce current through these, then we're going to see the movement of these electrons in a very specific direction. It is easy to make free electrons move through copper in a controlled manner. The movement of electrons in this manner is, and we're going to call it, current flow. Materials that have many free electrons are, and this is what we're talking about, what make up conductors. Then we have these devices called semiconductors. They are neither good conductors nor insulators. And the outer shell looks kind of like this. They have 4 electrons in their valence shell. They're not good at insulators, not good at conducting, so what are they good for? Well, silicon and germanium are examples, and they are good for lots of things. These materials are used in the manufacture of transistors, integrated devices, microprocessors. Microprocessors would be impossible without these things we call semiconductors, and many other electronic devices. These materials are usually doped to gain their unique conductive properties, and we will be looking at these later in this particular text. Then we have superconductors. These are materials that exhibit superconductivity. They offer no opposition to current flow and are essentially perfect conductors. To date, the only example of this behavior has been demonstrated at super cold temperatures. We're talking about 196 degrees centigrade, minus 196 degrees centigrade. So superconductivity has been attained. This is current flow with no resistance. However, the temperatures that you do it at are just absurdly cold, and they haven't been able to do this at room temperature. If they could do this at room temperature, this would revolutionize the power industry, because power could be moved with no resistance, and this would cause your electricity bills to drop dramatically. At least I think it would. Okay, many researchers are investigating room temperature superconductors. And okay, attraction and repulsion by charges. Like charges repel each other, unlike charges attract each other. And we've been talking about that in terms of atoms. Here you have no charge. Here we have two like charges that are going to attract each other. Two unlike charges are going to attract, and 2 like charges are going to repel. This is kind of like if you had 2 magnets with a north and a north pole here. They are going to repel from each other. And if you had a north and a south, they're going to be attracted to each other. Okay, units of measure for charge. Units of measure for charge. Charge is measured in a quantity we're going to call a coulomb. Coulomb is shown by a capital C. 1 coulomb is equal to the charge caused by the accumulation or deficiency of a bunch of electrons. And the number is 6.25 times 10 to the 18th power, and that is the number. It takes that many electrons to have 1 coulomb of charge. And the symbol for charge is the Q. And so Q equals the number of electrons divided by this value, 6.25 times 10 to the 18th power. So you've got to have a lot of electrons in order to get a Q. And your text has a couple problems to solve for charge. Now, coulombs is not something you typically talk about in electronics. We're going to find that coulombs has a direct relationship to amps, which is what we usually talk about when we talk about in terms of evaluating electricity. Voltage. Okay, defining voltage. When some distance separates 2 bodies with unequal charges, there is the potential for doing work. Okay, it says when some distance separates 2 bodies with unequal charges. So if we had a positive charge and we had a negative charge, and we brought them in fairly close proximity of each other, and we put connections on it, we could call it a battery. The difference in charge between any 2 points is referred to as a difference in potential. And so here we have a difference in potential, the positive and negative charges. Potential difference is measured in terms of voltage, and the unit of measure is the volt. And so if this is a, I don't know, we'll pretend this is a 12-volt battery. Electromotive force, EMF, is the potential difference that remains between points while charges are being transferred. Okay, EMF. Potential difference that remains between points, and the critical point here is while charges are being transferred. Now, next slide, we'll talk about this a little bit more. Here we have a battery, and batteries don't usually arc like that, but I like this this kind of a neat image. This battery illustrates the two separate charges in a battery, and we'll say that this is the positive side, and they'll say this is the negative side. The difference of potential provides the ability to move charges. So we can move charges between these 2 points in the battery and hence do work. This difference is measured in volts. A potential difference that is maintained is called an EMF, or an electromotive force. Now notice the key word here is that it is maintained. A lightning bolt that discharges to the earth has a large difference of potential, but it is lost in a moment of time. A battery can maintain this potential difference over an extended period of time. So in this case, you know, if we say we connected, let's pretend that we connect a light bulb. Okay, here we've got a light bulb connected here, and we have light. And we'll have light for an extended period of time. The battery will probably last for a few hours, and we'll have some light. And this is an extended period of time, so this battery is providing EMF. Now, in contrast, a lightning bolt has tremendous voltage, but it is all lost in a moment of time, and so that lightning bolt provides no EMF. Current flow. Okay, we talked about this earlier. We're going to look specifically at a copper atom because it is one of the probably one of the major conductors that is used for transferring electricity. And copper has, notice it has 29 electrons, 29 protons. Remember, the electrons are the positive, or excuse me, the electrons are the negative, and the protons are the positive, and the neutrons are neither. And so the protons and the neutrons, they're hanging around down here in the nucleus, and the electrons are out in the various shells. And copper, let's see, for copper it's 2, 8, 18, 1. So in this first shell there are 2, and then in the next one there are 8, kind of like this. And in the next one, I'm not going to draw them in, but there's 18 of them over here. And in the outer shell, the important one we're just looking at right here is the 1 that's out in the outer shell. At room temperature, enough thermal energy is present to ionize many of the copper atoms, giving copper an abundance of free electrons. So at room temperature, there's sufficient energy so that this guy is able to move. And he's probably just going to move over to the valence of another copper atom, but this valence electron is free to move. Current flow. Okay, so here we're talking about that. Actually, this electron here is what we're going to be talking about when we look at current flow. When opposite charges are placed upon the ends of the copper wire, the EMF causes the electrons to flow. So here we have a piece of copper wire, and I guess maybe I'll draw a little picture here. Here we have a power supply. This will be the positive side. This will be the negative side. And we'll have, let's put something here. We'll put on the light bulb here. And okay, when positive charges are placed upon the ends of the wire, the EMF causes electrons to flow. So those free electrons that we were talking about that are in the outer valence of the particular copper atom, now they've been given some EMF, and now where they were just moving kind of randomly. Now they're going to flow in a very specific direction, and in this case they're going from negative through the light bulb, and they're going to heat up the light bulb. It's going to radiate light. I'm not talking about light bulbs now, but anyway, you get the idea that current is going to flow through this wire because of the free electrons. Current flows from negative to positive potentials is called electron current flow. And so when we see current flowing from negative to positive, we're referring to it as electron current flow, electron current flow. Now, in some cases, current flow is represented as the movement of positive charges. Now, some will view the movement of electricity as charges going from positive to negative, and this particular school of thought is referred to as conventional current flow. Now, this is one of those things that you're neither right nor wrong on. It's the current actually flows at the speed of light, and no one really knows which way current flows. There's been considerable debate among in circles of electronics, but there's no consensus on which way it really goes. I tend to believe in electron flow simply because that's what I was taught when I began my study of electronics. I work with some other faculty who are convinced that it goes the other direction, but let everybody be convinced in their own thoughts on this particular subject. And here we have a picture, here we have a battery, and here current is starting on the negative post and going to the positive post, and this is referred to as electron flow. And here current is viewed as the movement of positive forces from the positive to the negative side, and they call that conventional flow. And again, there's not a consensus of the either way is fine for discussion purposes. Okay, unit of measure for current. Current is the movement of charges in a conductor. It is the measure of the number of electrons that flow past a given point, notice, per second. 1 amp is the amount of current that flows when 1 coulomb flows past a point in 1 second. Now it's expressed with the equation I equals Q over T. Now remember, we talked earlier about what was Q, and we said that it was 6.25 times 10 to the 18th, and this is over time. So if we have this many electrons flowing through a given piece of wire, and we have this much flow in 1 second, that is equal to a current, and current is usually represented with the letter I, of 1 amp. Now, in future discussions, we will, most of the time when we talk about current, we don't refer to it as the number of electrons. We simply refer to it as amps. But this gives you the foundational picture. Well, where do we get this term amp? Well, it comes from the definition of a coulomb. So current technically has to do with charge divided by time, and we refer to that as amps. And so here we have a little more discussion about the unit of measure for current. We say that 1 amp equals, and this is this formula we just talked about, Q over 1 second. When we say 1 amp of current in a wire, it means that 1 coulomb of electrons is flowing through a given point in the time of 1 second. So in this case, here we haven't talked about Ohm's law yet, but 10 volts over, in this case, 10 ohms, so this would be E over R would equal I, and in this case we would have 1 amp. The circuit above illustrates 1 amp of current flowing in a circuit. Okay, resistance. Resistance is current flowing through, current flowing through a circuit encounters opposition. This opposition is referred to as resistance. For current to flow in a circuit, an EMF must be applied that overcomes this opposition. And the unit of measure for resistance is measured in ohms, and this little symbol right here, and that is the unit for ohms. The practical range of resistance values used in electronics extends from thousandths of ohms to millions of ohms, and that in that terms megohms. So we have terms of milliohms indicating thousandths of ohms to millions of ohms, and we refer to those as megohms. Okay, I'm going to stop at this point. We're going to pick up right on the discussion of Ohm's law. Ohm's law is going to show us some relationships between voltage, resistance, and current, and we will be looking at those in the next lesson. This is 2.1a. Please continue on with 2.1b.